Hi guys, and welcome to your second tutorial on the first chapter of current electricity. So where I left you was conductance, which is the reciprocal of resistance. Now I'm just going to be talking about ohmic and non-ohmic resistors. The basic difference between ohmic resistors and non-ohmic resistors is that ohmic resistors are nothing but the resistors or conductors which follow or which obey the Ohm's law. I'm sorry about my handwriting. So ohmic conductors, they obey Ohm's law, which is nothing but the current flowing in a conductor is directly proportional to the potential difference across its ends, and this one does not obey the Ohm's law. So this basic difference, if at all it is asked in the paper, then you must write this. Second, let's talk about graphs now. Guys, I think you've done this in the past 2-3 months. That this is I've plotted a graph which here is the y-axis and this is the x-axis, and this is the VI graph. Now guys, if you remember, V is equal to IR, then V by I is equal to R. And last year when you did graphs in physics, then V by I in this case is nothing but the slope of this graph. Okay, I hope you understand that. So V by I for an ohmic conductor is a straight line. That means V by I is this, guys. This is your theta and tan theta. That means this particular thing upon this is equal to your slope. So guys, whichever one you might consider, then the slope its slope is constant. So this right here, it's a straight line. So that's what you call a VI graph. So graph for a VI potential V versus I is a straight line in case of an ohmic conductor, and for a non-ohmic conductor, guys, I'm not going to be drawing it, but the VI graph is not a straight line. Alright, so that's the basic difference between V and I. If you don't get the slope thing, don't worry, it won't be tested. The only thing you need to understand is the VI graph for an ohmic conductor is a straight line, whereas for a non-ohmic conductor it is not a straight line. So it's something I don't know, so just forget about it. It's not a straight line, this one is a straight line. So third difference, or the other ones I've given in your book, is regarding the slope. So slope of VI graph is always constant, and slope for non-ohmic conductors is not constant. So it's different for different values of V and I. So guys, that's pretty much about non-ohmic conductors. The only thing left to learn here is the examples. So all metallic conductors, like I named earlier, silver, copper, aluminium, and all metallic conductors are examples of ohmic conductors, whereas non-ohmic conductors lie or junction diode. I still remember these. Junction diode, yeah, diode valve, triode valve, and the filament of a bulb. Just remember this, guys. There's nothing much here. We done with this. Superconductors, guys. Another thing that is not really tested, but all you need to know is that superconductor is a substance of zero resistance at a very low temperature. So all this, guys, just don't do an exam-oriented study all the time. If you do have time, then look at all these things as general knowledge. Might just be asked later if you are taking science or if you do attend other competitions. So now I'll move on to specific resistance or resistivity, which is a very, very, very important topic. Considering our exam. So guys, what exactly is specific resistance? So as the book tells you, resistivity of a material is the resistance of a wire of that material of unit length and unit area of cross section. All words in this definition are extremely important, and let me just go through this topic with you. So guys, as we all know, as I told you in the last tutorial, resistance is directly proportional to the length. Resistance is also inversely proportional. This is how you denote the inversely proportional signs to the area. Now if I combine these two, then I get that resistance is directly proportional to L by A. So guys, as I told you in the last tutorial, whenever you want to remove the proportionality sign, which is this, you just insert a proportionality constant. So R is equal to rho L by A. So guys, this rho right here is a proportionality constant. Prop const. Okay, so this is a proportionality constant, and rho is denoted this way. So it's just like a P, and this is how you. This is the basic specific resistance sign. So this is what resistivity actually means. So if you want, then you can say that rho is equal to R A by L. Alright. Now what you need to know here is that you will be given questions like if the length of a wire it gets doubled. So what exactly do you mean when he says that the length gets doubled? What is kind of convey is that if you have a wire of this length, then the new wire is of this length. So if this is 1 meter, and this is 2 meters, okay, and the area is the same. So this is double length. So now what happens, guys, is that if you have a L here, the initial one, the new L is a 2L, and similarly, if you have a double length, guys, as I told you, whatever I told you right now, but the area was wrong, because actually when you stretch it, then just remember that you're stretching the same wire. So if you're really stretching it to a to a longer length, then your area will also reduce. So area of cross section, in case the wire is stretched to double its length, will get halved. So the total, so the new resistance will increase to 4 times its previous length. So guys, this is on page number 192 in my book. It's very easy. Please go through it in the book if you really want to. Very easy, and I'm sure you will understand this. If you do have problems, then please approach us, Karun, or me, or your lovely teachers at school who are amazingly good at the subjects that they're um, assigned. So guys, now let's move on to factors resisting resistivity. I'm not going to be writing anything again in the book. Dependence of resistivity on material of the conductor. All these pages are extremely important, guys. So material of the conductor, guys, as I already told you, resistivity is less for a good conductor. Same way, just think of resistivity as resistance in this case. So for a good conductor, guys, a conductor which conducts electricity, the resistance will be very low. And for a bad conductor, for a bad wood or rubber or glass or plastic, which is an insulator also, which is also known as an insulator, the resistivity or the resistance will be very large. For metals and alloys and semiconductors, it's given in the book. Please cram it up. That's what my advice to you, because sometimes it just might be asked. And dependence of resistivity on the temperature is nothing but resistivity of metal which increases with the increase in temperature. So if the temperature is increased for a metal, then the resistivity will increase. However, if you take a semiconductor, temperature increases and the resistivity increases. Guys, why I'm rushing through this is because we will be uploading worksheets also, and if not uploading, then we will be giving a some material later sometime. Then we will be solving such questions also, and we do expect you to be looking at your books at this point of time. So, guys, resistance and resistivity, I hope you've understood this. Conductivity is just like conductance, and conductivity is reciprocal of resistivity. Alright, now choice of material of wire. Please put a very important sign in front of it. I hope your teacher has already told you to do that, because it's very important. Please go through it. It's nothing but common sense, and if you don't understand anything, then you should approach your teacher, whoever you feel can explain such certain stuff to you. So now, guys, let's move on to the second section. Questions. I think in my book there are 3-4 examples, and sorry, 5 examples. Very important and very easy. Also, please go through them. Second section of this chapter discusses electromotive force, terminal voltage, and internal resistance. In very brief, I will go through this with you. As electromotive force, also known as an EMF, all right. It's not actually a force, all right. So please don't confuse yourself with the force. But what I'm going to tell you is that when the cell is in an open circuit, So the potential difference between the terminals of the cell at that point of time when the cell is in an open circuit is known as electromotive force. Alright, and EMF of a cell depends on two factors. Very, very, very important. Favorite question. It depends on two factors, which is material of. Please, you can't just say material. You have to say material of the electrodes, because the teacher might say, "Oh, what of the electrolyte?" However, in this case, both are in consideration. So, material of electrodes is the first one. The second one is the nature of the electrolyte. Right, guys? So I'm just writing this so that you know that what I'm talking about, and that's about it in EMF. So EMF can also be defined as the energy spent or the work done, guys, in taking a unit positive charge or a test charge around the complete circuit of the cell. Okay, inside the cell and outside the cell. That's what you mean by when the cell is in an open circuit. Alright, and terminal voltage is the complete opposite in the sense that when the circuit is um, you know when current is drawn in a cell, that means when the current is when the cell is in a closed circuit, right? So at that point of time when the cell is in a closed circuit, and when we discuss potential difference that time, then we're talking about terminal voltage. So that's pretty much about it. On page number 198 in my book, there's certain stuff. So you just need to go through all of this. I don't really think you will be asking questions, except for distinction between EMF and terminal voltage. That's the differences between them. EMF, as I told you right now, another characteristic of it is that it's the characteristic of the cell. So when you have a Daniel cell or an electron shell, I think this is given in your book too. The EMF is fixed; it will not change, guys. However, terminal voltage will depend on the amount of current which is drawn from the cell. Okay, and EMF, guys, is always greater than terminal voltage, whether the cell is open or closed, and terminal voltage is always less than the EMF. However, when the circuit is closed and when the circuit is open, I think when no current is drawn from the cell, it is equal. It can be equal to the EMF of the cell. So EMF and terminal voltage maximum at max will be equal, and EMF will always be greater than the terminal voltage. Otherwise, that's pretty much about it. And now let's move on to internal resistance of a cell. Very, very easy. You will just be asked questions on this, questions as in numericals. So just a very brief revision over internal resistance. Often, guys, in your paper, when you have circuits like this, I'm just going to be drawing the cell portion of it, and you have such a representation. Alright, and there's a dotted box right across this, and then there is an e written, sorry. I hope it is already discussed this with you. This is actually the EM of the cell, and don't confuse it with the voltage, because in certain numericals at this level you will be differentiating between terminal voltage and the EMF. Okay, so that's the basic difference between EMF and terminal voltage. Now let's move on to the internal resistance, guys. This resistance that's indicated inside the box is the internal resistance. So in other words, the resistance offered to the current inside the what do I say, inside the cell is known as the internal resistance. Right, guys? So this is what internal resistance means, and this V, or the voltage drop, guys. So the terminal voltage inside the cell is known as voltage drop. Small v is equal to I small r. Small v is equal to I small r, and capital V, as we already discussed, is equal to capital I. The I is always capital, and capital R. So that's what we have in terminal voltage and voltage drop. Last things to be discussed are factors affecting the internal resistance of a cell. Oh, yeah, guys, the formula, which is E by V minus 1 whole times R, is something that you have to do on your own. It's a very easy formula. The derivation is very easy. I'm not going to be doing this right now with you. I hope your teacher's already done this with you. Just go through it once, and numericals are also very easy. If we do have time, we will do certain numericals with you too. But another important thing is the factor affecting the internal resistance of a cell. First one is the surface area of electrodes. Second one is distance between electrodes. Third is nature and concentration of electrolyte. And the fourth is temperature. Now, larger the surface area, less is the internal resistance. So if the surface area of the electrodes is more, then you have a lesser internal resistance. and if you have more distance between the electrodes, then greater in the internal resistance. Now how I remember this is that if you have a larger distance between the electrodes, guys, so quite obviously the current has to travel a larger distance, and just consider this larger distance length to be traveled. Now as I told you, R is directly proportional to L, so if there is a larger length, there will be larger resistance. So same way, if the distance between the electrodes increases, then your internal resistance also increases. And third is nature and concentration of the electrolyte. So higher the concentration, greater is the internal resistance. Another thing that you have to learn up. Temperature is the last one, which is higher the temperature of the electrolyte, lower is the internal resistance. Alright guys, that's I think we've come to an end with this, and combination of resistors I'm not going to be doing with you, because I think this is something you should be knowing, and if at all you do have problems with this portion, then please consult your teacher, or please consult us. uh, Guys, it's very easy. Series just means that you just add up all the R's, and parallel circuit just means that you add the reciprocals and then reciprocal your answer, and that's where you have your answer. I think your teacher must have done the derivations with you. I don't know if they're in the syllabus. Please go to cisce.org. That's where you find all your test papers, guest papers, and syllabus for your 2013 board examinations. So guys, with that, I think I'm just going to be saying goodbye to you. And once again, I'm really sorry. I really don't have time. I have to finish a lot of tutorials today. So please bear with me. However, we do promise you we will come up with even better tutorials in the second term. So, however, I'm not going to be going now, in the sense that I'm going to be doing new tutorials. So I'll see you there. Thanks, guys.